something. So yeah. What so it's like the third time that I've done that. Brad right there, yeah. We're at one. Oh, thank you. You're welcome. Unless Cuss wants to give me her seat. Out of cousins. We switch. Actually, this is fun. I don't know. Oh, okay. Okay, cool. Ready. Oh, I don't know. Go to this school. I might.
Where's my online people?
Oh, yeah.
You happen to see anybody try to join in, just admit them, I guess. So I don't know where they are. Welcome back, everybody. How are you doing today? Are we excited? I'm excited. I'm so excited. Are you guys? For an entire marathon lecture? Oh, learning physics.
I just think that I've got today, is that something that I can do, or
Not during class, but right after class.
I don't have time to talk.
Oh,
Wait, can I come in before school or
you
something?
can take it tonight. When do you want to take it?
Oh, I'll take it.
Discord me.
I'll come in early tomorrow if that's good.
Okay. Oh, here. Hey, some people are coming in.
I don't have
There we go. There we go. There we go. Should be one more eventually, but I don't know. We'll see. There he is. Okay, now they're all in. Okay, hopefully all you online people can see the board. And hear me good enough. I'm going to try this. If this doesn't work, you're going to have to let me know, I guess. Okay, we are on whatever page it says is the NASCAR inquiry. NASCAR inquiry. It's a nasty inquiry. 2 full pages of inquiry. 2 block days of lecture and notes. Today's the first day of the rest of the year in physics. No, I would also act positively. You acted positively. What's the other course? I reacted negatively. Does my eye look weird? Yeah, my wife tried to kill me last night. Well, I should have, I'm assuming. She should have said that.
Of the bowl of kiwi, that's my life.
I told her, she gave me a bowl of kiwi and I said, I'm pretty sure last time you tasted a piece of kiwi that I kind of had that like itchy sensation, that like, I could be allergic to it maybe. She goes, no way. So I ate the whole bowl of kiwi and then my eyes swelled completely shut. I was up all night with like ice on them and stuff and kind of walking around like this.
Do you have an EpiPen?
No, I didn't even think I had an allergy.
Well,
Apparently I might be allergic to kiwi. I should have told you that. Why did I tell you that? Now you're gonna take me out the way you're gonna take me out. I'm gonna find a little piece of kiwi all over my desk. So anyway, so my eyes might be a little messed up. That's why I told you. So, okay. So there's 3 parts to this inquiry. Okay, 3 parts. We're gonna get through, I hope, the first 2 parts today. And the 3rd part is a pretty nasty kind of derivation. And so we're gonna save that till Friday, or whenever we have Friday. Okay. So everybody see the page you're on? Yeah, we're doing it all together. Yeah. I'm gonna need someone to help up here. Yeah, I volunteered Dylan to help me run the velocity machine. Okay. You don't have to come up till I'm ready. Okay. So part one, we're going to, so this is all about driving around the track. The whole inquiry is about driving around different kinds of tracks. The first track we're going to drive around is just a regular circle track made of, I don't know, some asphalt or gravel or whatever you want it to be, it doesn't matter. But it's just a circle track, okay? And you're going to drive around it, and we want to figure out a velocity. How fast can you go around a circle track? We want to derive a physics equation for how fast, a critical velocity, that you can go around before you do what? Skid off, right? So fly outwards, right? Okay? That's what we want to figure out. Okay, now what are you have experiences. I know some of you probably have tried to go fast, even though you shouldn't. Okay, what are some things that would determine how fast you can go in a circle or around a curve? Traction, so like friction, right? How well you're trying to go around like this, you're trying to fly outwards, right? So the road and the tires have to grip on, right? Okay, and if it was like all of a sudden mu is 0, there was like ice all of a sudden, there's no way you're even gonna make the turn, right? You're just going to fly right out. Okay, so mu obviously has something to do with it. We would expect mu to be in this equation somewhere. What else? The normal force is how we would find the friction. So the normal force does have to be in here somewhere, right? We're going to draw an FBD to try to derive this equation. So normal force will definitely be in that.
Velocity.
Well, the velocity is what we're trying to figure out.
Oh, it is.
Right, so we're trying to figure out how fast we can go before we fly off. So mu is a definite factor. What else would be a factor?
The radius of the turn.
Yeah, how quickly you're turning, right? I mean, you know, if you're doing some big, huge, long, big, wide turn, you can go really fast, right? But if you're going around a short little turn real quick, you gotta slow down, right? Okay, so the radius, mu, definitely things that we should probably be in this equation. Okay, all right. So here we go. So we're gonna start with we gotta draw an FBD before we can do all these derivations. So I'm going to try to draw like the cross section of a track. So here's the car, and so it's kind of coming out of the board. We're going in that way. Does that make sense? Okay. I had a track like here, and I cut it down. And so here's the track car coming out of the board. It's going to curve around and go right in there, and it's going to come back out of the board. Okay. So I'm going to try to draw an FBD on there. So the device we're going to use is it's really hard to have an inquiry where I can have a little car that's actually driving in a circle. So instead, what we do is we put the car on a rotating platform, and then we rotate the platform, and now the car's driving in a circle, right? And I can figure out how fast the velocity of that car is going, right? This is actually measuring the angular velocity of the table, but we can convert that into how fast this is going in meters per second. So we're going to go see how fast it goes till it flies off, and then we'll be able to figure out the critical velocity and see if our equation works. Okay. So what forces do I put on this? Force of gravity, right? The weight, that always works down. So I got mg. Okay, what else?
So opposite that to normal force.
The normal force is everything on a surface. There should always be a normal force, a surface pushing back up on it. And what else? There's one more. And the hard thing is to remember that this isn't just sitting there. It's actually going in a circle really fast. So
I don't know how you express that.
which way is it trying to actually, we're going to go faster, faster, and faster until it does what? Flies outwards, right? So what's
friction.
keeping it from flying off right now? Friction. So which way is that working? It's actually working in, right? If this thing's coming out like this and it's trying to fly out like that way, right? The road is kind of holding on to the tires, right? Allowing it to keep going around. That make sense? Okay, so that's friction. So friction is actually going out like this. Okay, it's kind of gripping on, and it's allowing it to go around. Okay, those are all your forces. And the reason we always drew FBDs was because we were trying to figure out, is there a net force on the object or is there not? That's what we're always trying to figure out, right? We never drew the F net onto an FBD, ever. We drew all the forces and then we'd see if there was an F net. I could add a couple together and see what the overall resultant was. That'd be my F net. Is there a net force for this car?
Yeah.
Yes.
Yeah.
Could you have told me that there was a net force for this car before we drew the FBD?
Yeah.
Yes, how come?
It's accelerating the quantum.
It's accelerating because it's doing what?
Uh,
It's going in a direction, okay? So it's in a different direction. So the answer to that question, every time I ask it in the next 2 days, is yes, there's a net force. It's going in a circle. Anything traveling in a circle, there is a net force. And which way is the net force going? You even know that. It's going towards the middle of the circle, always, okay? Lots of questions about that on the Drake exam. In fact, that was one, right? You have a velocity and the centripetal force is perpendicular to that velocity, right? So anything going in a circle, there's automatically a net force. We don't even have to draw an FBD to prove it. We just know that there is, and we know which way it's going to. Okay. Now we draw the FBD, and we can clearly see there's a net force because this one and this one would have to be equal here, wouldn't they? Because it's not accelerating up or accelerating down, right? So they have to be balanced, and that leaves only this one left over. And there's only one force. That's a net force, right? So this friction is your net force. So then you always write an equation, F net equals, and you write everything that's the net force, would be the friction. Okay? Remember when we used to do that? F net equals whatever. And what did we always plug in for F net? MA. Now what do we plug in for F net? Because MA was when we were going in nice lines and speeding up and slowing down. Now we're accelerating by changing our direction. So what do we put in for F net now? Who remembers? It's still M. Had to use this equation probably like 5 times at least on the Drake exam. MV squared over R, centripetal force, right? Remember that? Been too long. Okay, so in for F net, we're going to put MV squared over R, not MA, MV squared over R, which is really actually MA, because V squared over R is centripetal acceleration, right? Your acceleration vector towards the middle. So MV squared over R is your F net. What's the equation for friction? Who remembers that? Mu Fn, right? Mu Fn, everybody remember that one? Okay, mu Fn, what's Fn in this FBD? Yeah, it's the weight. So mu mg. And you'll notice the mass will cancel out. You'll notice mass has been canceling out in every derivation we've been doing in this unit, right? Pretty much. And it's going to cancel out in every other derivation we do all next 2 days also. Okay. So what do I got? I have v squared equals mu. So the critical velocity is the square root of mu. That's it. That's an easy one. You want to know how fast you can go around a circle with your car? take the radius of the circle, whatever you're going around, times mu. It's gravel in your tires or asphalt in your tires. You got to know what the mu is. And gravity, square root the whole thing, and you'll have your velocity. That'll be in meters per second. You might want to convert to miles per hour or something. That's critical velocity for a flat circular track. Have you got it? You have Jedi trial questions, you have ELAB questions, someone going around a track with the mu of whatever. How fast can they go? That's the equation you use for that. It's on the front of your book. You know how to do it. Okay? The first one's easy. They get a little more complicated. Okay, so what we're going to do is, I'm not going to use this little car right here. We're going to use this weight right here, an unknown mass. Actually, I know the mass, I think. But we don't need to know it, right? Because it canceled out. So I'm going to put it right here on this. I have a little dot right here that tells me that it's 20 centimeters from here to here. 20 centimeter radius, 0.20 meters. Okay. And I'm going to start spinning this until that thing becomes taut. Okay. It's going to try to fly outwards. I didn't want to kill anybody, so I hooked it on the center. Okay. As soon as that starts to go outwards, we're going to stop and measure what the velocity is. Okay. Now, you'll notice, oh, that's terrible. What is that? That is not possible.
So fast.
Like the speed of light or something. Okay. You'll notice here that this velocity is in radians per second. Okay. So, side lecture. Okay. The next unit is 4.3 is rotational motion. Okay. And someone in the last class asked, what's the difference between circular motion and rotational motion? If I spin this, what's that thing doing? No, it's not rotating. It's moving in a circle. If it was a pen, it would be drawing a circle underneath it, right? But what is this table doing? The table is rotating. Okay, the axis of the whole object is, this is rotating, right? This is moving in a circle, right? But this is rotating. That's the difference between the two. They used to be one unit. Okay, and I don't know, people had problems deciding whether it's rotating or whether it's going in a circle, so I split them up. The problem with splitting them up is that sometimes to get something to go in a circle, I got to put it on something that's rotating, so you need to understand a little bit about rotating things. Because the velocity here is the velocity of how fast this is rotating. It's radians per second. It's not meters per second. Okay, it's how fast it's actually rotating. It could be in revolutions per second or degrees per second. It happens to be in radians per second. And I need to be able to convert that to figure out how fast is any object at whatever radius, how fast is it actually going in meters per second. That makes sense? So to understand that, we have to understand something called a radian. Raise your hand if, don't tell me anything. Raise your hand if you think you totally understand exactly, could lecture on it, what a radian is. 2 of you? 2.5? Okay, good. All right, so you guys will answer all my questions. Okay, so I'm going to lecture on it just real quickly. Okay? And you'll see, then at the end, you can tell me if you just knew everything. Yeah. Okay. So here we go, ready? Thousands of years ago. The same response I've gotten in every single class. It's like grown. Okay. No, literally, thousands of years ago, people were fascinated with a certain shape. It was called a circle. Okay? Little circles, big circles. Blue circles, red circles. I just made that up. It's kind of like duck research. Okay. So what they decided to do, what they thought was really intriguing is if you draw a measurement, make a measurement from the center like out to the edge. Take the center of the circle out to the edge. Take that measurement, right? And the Greek for measurement was called meter. You know that? That's where we got the word meter from. It means a measurement. Okay? So the Greek for the measurement was a meter. So this is a meter. And then some of them said, well, no, let's not do that. Let's take the distance all the way across. 2 measurements, not just a single measurement, but let's take 2 measurements, which they called a diameter. 2 measurements, right? And let's just take a distance across, and even this one is obviously a smaller distance, right? It's a smaller circle. Put a string on it, cut it off so you have a length of the distance across the circle. I wonder, with just 1 sig fig, I wonder approximately how many, to the nearest whole number, how many of these little diameters could you always put around the outside of a circle? It doesn't matter if it's little or if it's big. If it's big, I take this and I drape it around. I take this little one, I drape it around. I wanted to see, or they wanted to see a long time ago, what's the ratio of the outside distance to the across distance? How many of the crosses can I put around? And the answer with 1 sig fig was, you can put about 3 of them, a little over 3 of them actually. It was everybody was kind of hoping it'd be some golden ratio and be exactly some number, magic number 3. Okay, but at the beginning, that was close enough for their good measurement skills. It was about 3. So everybody knew that if you take the measurement across a circle, you can put 3 of those measurements around the circle. 3 of those dia measurements, technically. Which means how many measurements could you put around a circle? About 6, a little over 6, right? You put 6 of them around a circle. 6 radii lengths would go around this circle. Okay? Does that make sense? Okay. So if you take a radius and it's rotating around, and then it rotates how far? It rotates like right to here, so that it sweeps out the exact same length as whatever that radius is. So it sweeps out a whole radius out on the outer edge. That makes sense? Okay. That would be like a piece of the pie here. That'd be an angle, okay? And a lot of times we're used to angles being in degrees, right? Or parts of a turn, or however you want to do it, okay? This angle right here would be called 1 radian. 1 radian. A radian is the angle that would sweep out a radius out on the outer edge of the circle. That make sense? And how many of these angles can you have in a whole circle? About 6, right? A little over 6, okay? So I always think when I play Trivia Pursuit, I always like that little game piece because it's kind of like each one of those is like about a radian, right? Each little piece of pie is a radian, about 6 radians. Now technically it's a little bit more, right? They measured more precisely, how many of these diameters go around the perimeter. It was 3. And the big mistake that they made was they decided to take that number, that ratio of the perimeter to the cross. They took that ratio and they assigned it to a Greek letter. And then everybody stopped remembering what it even was and forgot everything about it. What Greek letter did they choose? Yeah, they chose a Greek letter called pi. And they said, pi is 3. Okay, pi is 3. Right? Gravity's 10. Pi is 3. That's all you have to know. Really. You got to call it. Okay. So then they more precisely measured it, and they found out it wasn't exactly 3, which was disappointing to a lot of them. It was a little bit more. They got a little bit more precise, and they found it as 3.1. Right. So they used that for hundreds of years, and then it was 3.1, 4, and then now they have digits all the way crazy out. I don't know how many you can remember, but that's all I can remember. 3.14. There might be a 1 and a 7 after that. I'm not sure. Is it a 1.5? Okay. Yeah, see, I don't know. 3.14 is good enough for me. Or I just hit the button on my calculator. Okay. So this is the ratio of the perimeter to the across, is what that Greek symbol is. Okay. So how many radii can go around a circle? Technically, it's not 6, it's like 6.28, right? Or what you might call twice pi, right? Okay. All right. So that's Correct, yes, because you take 2 pi and you multiply it by how long a radius actually is, right? Which is exactly what we're trying to get to. If this is in radians per second, let's say it says like 3 radians per second. What does that mean? How fast is that going? How fast is this going? It's 3 radians per second. Yeah, in 1 second, it would go like that far, right? It'd turn around 180 degrees, right? Or 3 radians, technically. Does that make sense? Okay. So if I want to figure out how far, like, by the way, 1 radian would be approximately how many degrees? What's the correlation there? I mean, how many degrees? Yeah, about 60 degrees, right? I mean, this is like 1 radian, like six radians in a circle, give or take, you know? And so you take 360 degrees in a circle, right? Divided by 6 would be like 60 degrees. Technically, it'd be like 57 or something, I think it is. 57 something degrees, right? A radian is the same thing as like 57 degrees. Okay, I just always think 60 degrees. I just round everything off to 1, so it makes it nice and easy. Okay, but if I'm turning around a certain amount of radians per second, if I want to know how fast something actually like that's rotational. That's rotational. But we're looking at circular. So if I have an object on it and it's traveling, how many meters per second is it going? That's an easy thing to figure out. If I know this object is rotating at like 3 radians per second, to figure out how fast this thing's going in meters per second, all I have to do is what? Multiply by whatever the radius is, right? So you would do dimension analysis. 1 radius is like, I don't know, maybe it's a 2 meter radius circle. 1 radius is 2 meters, so it'd be 6 meters per second. Okay, so if this thing was traveling at, what does it say it was? We'll get it going here. Okay, it's like, 2 radians per second. If this thing is on the 0.2 meter mark, how fast is it actually going? It'd be 2 times 0.2, right? You just take it times the radius, take the angular velocity of the rotating thing times the radius of how far the thing is on it. What does that mean if something's further out on it? It'd be going faster, right? I would take a bigger radius times the same angular velocity. I think that was a great question too, right? The merry-go-round is going at a certain angular velocity. But someone here on the merry-go-round, opposed to someone here on the merry-go-round, they're both going the same angular velocity, radians per second, right? But they're going different meters per second, right? Linear velocities. This one's going faster than this one. Does that make sense? Because it has a lot farther to go, right? It's a bigger circle, but it's the same amount of time, right? Much farther to go, same amount of time. So big meters per second, smaller meters, it's smaller all the way to the middle. Does that make sense? So in all these inquiries, the computer is going to measure the angular velocity of the thing. That's not what I want. For this unit, next unit, I do want that. But for this unit, I want to know the circular motion of this thing. So I have to take the angular motion times the radius of where it's at. This used to be an amazingly fun amusement park ride called the Whirling Platter. It was a big, huge disc, and you just go and you sit on it, and then they would start spinning it faster and faster and faster until everybody flew off. It was like a big, huge floor out here, so you'd fly off,
Oh.
And if you knew physics, you got on it, where'd you go sit? You tried to sit in the middle. Now, you couldn't sit in the exact middle, because that'd be really dangerous, because you'd be like going so fast until you flipped over and killed yourself, probably. But there was a kind of a hub in the middle, so you could get quite a ways out there. You couldn't really hold on to anything, and it would go faster and faster. And the people that didn't know physics, we'd always laugh at them. They'd get on, they'd sit out here on the edge, it starts going, they fly off, their ride's over, they're done. Couldn't get back on once you flew off. So some people would be out here a little farther, but they'd all just kind of take off. And the people in here, get going really, really fast until they couldn't hold on anymore. And depending on what clothes you wore, then you fly off, right? Whirling Platter, a lot of fun. New physics, you knew what to do, you knew how to write it. Okay. All right, so first thing we're gonna do is we're going to take this object, we're gonna put it 20 centimeters, and we're going to rearrange this equation, actually, to find mu, okay? Because then I'm gonna move it to a new radius, and I wanna be able to predict the velocity. So before we do that, I gotta figure out what is mu between leather and tabletop, okay? I don't know what the mu is. So the first experiment we're gonna do is actually figure out what mu is. So how many of you can look at this equation, not write anything down, and in your brain, do the algebra to figure out the equation for mu?
Oh, sorry.
Can you do that? Try to do that in your brain without writing anything down. You should always kind of practice that. That's a good skill. Square both sides, right? So you have b squared equals gur mu, right? And then you do what with the g and the r? You put it on underneath the other side. So it'd be b squared over gr, right? Okay, u equals b squared over gur. There's our equation for mu. We're going to figure it out real quick. The radius is 0.2. The gravity is 9.81. We don't know what the velocity is, but we're gonna figure that out right now. Okay. All right, Dylan, you're up. You can bring your whole chair up if you want. You can just roll it up there. I know you probably wouldn't want to stand up. Okay. And I don't know what's going on, but okay, it's already going, so you're all right. So you're gonna have to click on the stop the moment that this thing starts to fly out. The moment this gets tight. I'm gonna yell, I'm gonna scream. Okay, so you'll know exactly what it is. It's really hard to do it on this one because it's kind of gradual. Okay, I got some better stuff later. So. Stop. What'd you get? 4.01. Okay, so what do I do with that? I got to multiply it by the radius of where it was when it started flying out, and that was 0.2, right? So 4.01 times 0.2, right? 0.802, that's meters per second. Okay, we're going to square that. I'm going to divide it by 9.81. I'm going to divide it by 0.2, and I get a mu of like 0.328. Okay. Now, if we were really worried about good science principles, we probably do that test, 4 or 5 more times, and then average all the mu's. So we were probably pretty good, but we're not going to do that. We're just going to pretend that we're perfect the first time. Okay. Arrogant physics. All right. So now what we're going to do is I'm going to put it on the 30 centimeter mark, and we're going to. This is exciting. This is really fun. We're going to predict exactly what we'll see on this computer when Dylan hits a stop. Okay? So we're going to use this as our mu. Hopefully it's right. Okay? We're going to solve for this critical velocity, right? Okay. So we're going to do square root 9.81 times the radius is now 0.3. We're to further radius out. What do you expect the velocity to be? Higher, right? You're further out, you can go faster before you fly off. Times 0.328. 9.81 times 0.3 times 0.328 equals square root is 0.982. That's meters per second. But that's not what the computer's going to say, though, is it? Because the computer is actually saying the rotational velocity of the disk. So how do I get to the rotational velocity? Divide by the radius. Okay. The sooner you can maybe write that down and remember that thing is going to be super helpful. Okay. If you're going from linear to rotational, you divide. If you're going from rotational, something rotating, to linear, you multiply by the radius. Okay. I don't know how you need to remember that, but that's going to get you a long ways in the next couple of Jedi trials if you do that. So I'm gonna divide this by, what was the radius, 0.3. And we should get 3.27 radians per second. Dylan can have fast fingers. No pressure. I will tell you, we did this twice in the first class and they nailed it perfect. Second try. Last class, never got it. We did it twice, 3 times maybe even. Never got it. Okay, we got started again. I don't know what to do. Yeah, keep doing it. It's no, it's there it went. I don't know. I just don't know what's going on there. Maybe it must be a delay or something. Okay, ready? Say you ready. You ready? We're looking for a 3.27. Stop. Ooh. Can I go again? I'll try not to yell so loud. I won't scare you. Stop. It's worse.
This guy doesn't have the.
What do you mean?
You want to go for it one more time? It could, I mean, you might not have been that great. In the last class, we did do it twice and averaged a mu. In the first class, we didn't. Nope.
It actually took a higher speed for you.
Keep going higher, bro.
Huh. Okay. Well, we got to do a percent error then. Which one was the best? What was the first one we had? Well, this is better. 3.42 and subtract 3.27 minus 3.27. And we're going to divide by 3.27 because that's what we predicted. That should be the math experiment or the theoretical. Now that's a 4.6%. That's good. That's good. It's really good. Don't feel bad. Okay. Questions on that? Part 1. Oh, by the way, there is a question on part 1. We should answer that. Let's see. Okay, what is the smallest radius in which you can turn your car if you are moving 65 miles per hour? And the coefficient of friction is 0.33. What are we solving for there then? 65 miles per hour is how fast you're going, and mu is 0.33. What's the radius of the curvature? The smallest radius you could turn and still be okay, not be flying off. I have to solve this for what? For R, right? Can you do that in your head? G mu, right? G mu. Okay. So 9.81, 0.33, and 65 miles per hour isn't going to cut it, right? We got 1 mile per hour. Here's your standard thing. I do this one a lot. 0.447 meters per second is 1 mile per hour. So we're going to take 65 and we're going to multiply by 0.447. We get like 29 meters per second. Okay. So you see this is really close to 0.5, right? So just in case you're curious, you're driving down the road in miles per hour. If you want to know meters per second, basically cut it in half, right? 50 miles per hour, you're going around 25 meters per second. Okay, just a quick thing for you there. You're curious. Okay, we're going to square that, divide by 9.81. Oops. 1 divided by 0.3. Yeah, I got like 260 meters. Okay, the radius. 261 maybe, around that up. Okay. So we got a part one, that's part one. We're gonna do part two, we're not gonna do part two. Part three is gonna be Friday.
Part three, there's derivation.
Yeah, well, there's derivations in both of them, but part three is not a fun one. Not as fun, I guess, maybe. For students, that is, for students. For me, it's ecstatic. It's like my favorite thing.
There are a lot of derivations.
Yes.
That's why you love it.
That's why I love it. Okay, so what we're gonna do now is, we're done with this thing, okay? What we're gonna do now is we're gonna imagine the car going around the track, okay? Car's going on the track. Now, if I turned off friction right away, mu is 0, that's bad, you're gonna fly off. But if I could actually then take the track, the road, and like angle it up like this, it wouldn't actually matter that there was no friction. You could actually maintain that and actually go around that. As long as it was banked. If it's flat, there's no way, you're going off, right? But if you bank it, okay, now the normal force, right, is kind of pushing up, so it's kind of pushing, over a little bit, right? Okay, right? So it's gonna hold you on there a little bit. Okay, so you could bank something and it would actually be able to still go around. So we're gonna derive an equation for the velocity to go around a banked turn. So we have a circular track, it's all banked. And you're just going around it like this, okay? The equation for the velocity of a banked turn without any friction, which basically means not reality. I mean, there's no situation where this would be real except for on a physics test. When I say you're going around a banked turn and you can pretend there's no friction, that's going to make it easier, okay? We want to derive an equation for that. All right, and then test it. The way we're going to test it is we're going to have this angle thing right here. I can make a ramp like this, and we can use a ball instead because rolling friction is like really low, so we're going to pretend there's no friction. And I can like have it out here like this, and I can just wait till it falls back down. And I know that's the critical velocity, right? See, it's going around a circle. Okay, does that make sense? So we're going to derive that equation. Ooh, actually, I almost forgot something. We got to do one more thing before we actually start this. I need something for NASCAR Part 3 on Friday. NASCAR Part 3 is we're going to have a bank turn, and we're going to have, a NASCAR Suburban going around the track, okay? And so with friction. So I actually need to find the friction between this rubber and this wood right here. And I need to do that the way we just did it with that other thing. So while it's flat, okay? So I'm gonna have to drive this car in a circle until it flies off, and we're gonna have to figure out get the velocity, and we'll be able to figure out mu. So if you remember, so V was square root of ver mu. So mu was V squared over GR. I need to figure out the mu, and we're just gonna set it aside for part 3 later, okay? So I'll need your help again here. I'm gonna spin it around till, let's see, I gotta remember what the radius is out from here out to the car. Is, never remember, I wrote it down, where is it? It's 23 centimeters. So it's 23 centimeters from the center out to the car. So the radius, so 9.81 times 0.23, and we need to square the velocity, and then we need to solve for mu, and we'll put it on like the second page. Put it at the top corner of your second page when we get it figured out. Okay, you got it going? Yeah, starting. Okay. This time you don't have to worry about it because when the car flies out and crashes, its horn's going to go off and its airbags are going to deploy. So you'll know. You think I was lying or something? I told you the horn was gonna go out.
That's scared me too.
Oh, wow.
We're expecting that.
How loud?
What part of the horn's gonna go off? Did you not understand? It's like,
How loud is it?
you guys think I'm always like just blowing smoke or something or what?
Yeah. I didn't even know you said that. I was gonna think so.
So you can slides out, hits the. Switch there. Okay, what'd you get? 5.03. Now remember, we gotta do what with that? Yeah, we gotta multiply with the radius, which was 23, so 0.23 times 0.23. There's your velocity. Square it. Divide by 9.81. Divide by 0.23. And the mu, 0.593. Maybe we should do that one again. Let's do that one again, average that one. We want that mu to be actually, fairly. Let's do good science. Start it again. We'll do one more and then we'll average them the mu's. Average the mu's. Mm. 4.78. Okay. 4.78 times 0.23. Square it. Divide by 9.1. Divide by 0.23 equals. I got a 0.536. I'm going to add 0.593 and divide by 2. Okay, we're going to use this as our mu on the second page. We're going to use 0.564 is the mu between the NASCAR Suburban's tire and wood. NASCAR track with wood. But that's somewhere on the second page up in the corner. We're going to need to refer to that later. That's, I think, is similar to what we got in the other classes. So. Okay, so here we go. We're gonna do the angled frictionless turn. So we're gonna use the ball, and we're gonna put it at different angles. We're gonna put it at 10 degrees first. And I want us to be able to tell us what this velocity is gonna say. I'm going to spin it really fast, and then it's going to eventually slow down. And it's going to fall, and we're going to stop it, and right when it falls, and we're going to figure out what the velocity is. Okay, so we got to derive an equation. This one's a little tougher. If I do a cross section of the track, now I have inclined planes. Right? Here's the car. Drive out of here. Going in there. Right? Okay. This is a little tricky because you know a lot of things about inclined planes, but this isn't your everyday inclined plane problem. This isn't something just sitting on the inclined plane. This is something that's actually, driving along the bank turn. So what are some classic things that go on all inclined plane problems, first of all? What'd you say first? You said normal force, right? There's always a normal, if it's on a surface, there's a normal. So the normal force is going up like this, right? Perpendicular out of the surface, okay? And then there's what? The weight, right? Yeah. Which way does weight go? Weight always goes straight down. But you remember what the problem was? What that was?
Normal force is perpendicular.
Yeah, we want all of our forces to be perpendicular and parallel to this inclined plane, remember? So remember what we did with the weight? Last class did a really good job with this. I was really surprised. It gets divided into its perpendicular and parallel components. You remember doing that or not?
Yeah.
Okay, so there was one weight component went like this and another weight component went like this. Do you remember what they were? Which one was which?
The down one is the cosine.
This one? Yeah. Yes. This one is mg,
Good job. I didn't
right?
remember that.
Cosine of theta. And this one's mg sine of theta. And of course, this is theta. right? Okay. All right, so that's good. That's what we got happening. There's no friction in this problem, right? So we're good, we're making this one an easy one. No friction, so I don't have to draw any friction on me. So that's it. That's all the forces on this car. Okay, so I'll ask you a question. Is there a net force?
Yeah.
I told you the answer to this question every single time. Yes, of course there is. Because why? Well, forget the FPD. Because why? Because it's going in a circle, right? Anything going in a circle is changing its direction, so it's accelerating. So there's a net force, right? Every time. Anything going in a circle, there's a net force. And which way is the net force going? You know that too. Always straight in towards the center of the circle. Not down, but straight in. Okay? So I know, and that makes this confusing. That makes this part kind of not seem right. I know that if I take all three of those vectors and I add them all up together, that it should result in a net force, and we don't ever draw a net force on the FPDs, but I'm going to do it now. It should, all three of these added together should result in a net force going this way, which of course I know is called centripetal force. That's what net force is, centripetal force, right? All three of these have to add up to that. What does that tell you about this that you might not have thought about before? In a regular standard inclined plane problem, what would you have thought about this force and this force? They should be equal, right? Are they equal now? There's no way they can be equal. Does everybody say there's no way they can be equal? Because this and this and this all have to add up vectorially to that. If this one and this one are equal, then the net force is right there and it's going down. It's not going straight out. So how do I add this one and this one so that whatever this one and this one added up, added to this one will give me something going straight out like this? That means the normal force has to be, it has to be something a lot bigger than this, right? Doesn't it? Okay. This has to be a lot bigger than this so that when I take that, subtract out that, I still have some going up like this. And then those two vectors would clearly be pull something over this way, right? That makes sense or not? Yeah. This part is the part that I usually lose 60% of people, I would say. Doesn't matter, you don't have to derive it, but it's cool if you understand it. So I'm gonna draw, so like pretend here's like the inclined plane. So I'm going to draw that force. So here's the car, and I'm going to draw that force going down right in there. Okay, there's mg sine of theta, and I'm going to make a right triangle here. Okay, what is this force then equal to? Because all three of these have to add up to give me that hypotenuse. So this one is that one. What would this one be? It's not the normal force. It'd be the it'd be the resultant of these two, which would be what? See, I told you. I had 70%, but I got 0 that time. So these three forces have to add up to give me this, right? So vectorially, which means tail head gives me the result, right? So I put this single vector right there. And this vector is going to be these two, right? So what can I write here for this vector? Right, yeah, maybe it was just too easy, maybe. This vector here would be normal force minus this, right? I'm going to combine these two. This one's bigger than that. So there's a net force between these two that are going up here, right? There's a net force coming down this, and there's a net force going up here. And I'm going to add those two net forces to give me my overall net force. So this right here would be Fn minus mg cosine theta. Yeah, is that kind of? Do you see that or not? Yeah. Okay. I don't actually, in this problem, let's make you mad, but in this problem, I don't really care about this at all. We're not even going to use it. Okay, because there's no friction in this problem, so I don't even need to know what Fn is. So I'm not going to use that in this one, but in the next one, see, we're going to have to use both of these sides. It's going to be worse. Okay, now, if this is my inclined plane right here, and this is my angle, then that means that angle is the same right there. Right? Alternate interior angles. Okay, and if that angle there, and I know I have FC and I have mg sine theta here, then I can write this. FC cosine of theta would equal mg sine of theta. Cosine of this angle, right, is the adjacent side over the hypotenuse. Cosine of this angle is the adjacent side over the hypotenuse. So that'd be the hypotenuse times the cosine of the angle would equal this side. That right there. Yes? Okay. What do you put in for the net force, or the centripetal force? Goes in for net force. It used to be MA, now it's keep trying.
MV squared over R.
There you go.
You know I got it.
There you go. MV squared over R cosine theta equals mg sine theta. The masses cancel like they always do, right? I can multiply the R over, and I can also divide the cosine under. And what would you get? V squared would equal G times R tangent theta. Sine over cosine is tangent theta. Critical velocity around a banked frictionless turn is the square root of GER tangent of theta. Square root of GER tan. There's another equation for you. Let's review a couple of equations. Anybody remember the equation for going, just barely making it across the top of a roller coaster? Square root of GER. That was the simplest one we have. Square root of GER, right? What is it going around like a dirt track? We just did that. That was inquiry 1. Square root of GER mu. Square root of GER mu. What is it going around a frictionless banked track? Square root of GER tan. Okay. NASCAR Part 3 will be going around a banked, be a real NASCAR track. Going around a bank turn when there is friction. What's the critical velocity? That won't be as pretty, but it'll be good. We'll get it done. Okay, so here's our equation, and we're going to use a ball to represent the car going in a circle, and we're going to do 3 trials. You can make a little chart on your table here at 10 degrees, 10 degrees, 20 degrees, 30 degrees. And I want you to calculate what's the velocity. And then I want you to convert it to the angular velocity, which we use the Greek letter omega symbol for. What's the angular velocity? The computer will tell us in radians per second. This is meters per second. This is radians per second. Okay. The radius of the ball is 32 centimeters out. So the radius is 0.32 meters. Okay, radius is 0.32 meters. So real quickly, we want to use this equation and we want to calculate all of our predictions for what Dylan's going to stop the computer on for us. .81 times 0.32 times 10 tangent square root. So this first one I got 0.744. Everybody else get that? Okay, how do I get to this? If I have 0.744 meters per second, I am linear velocity. How do you get to angular velocity? You divide by the radius. Remember, I said try to remember that. Which way? Linear to rotational or linear to angular is divide. You're going from angular to linear, multiply by the radius, okay? So I'm gonna take 0.744, I'm gonna divide by 0.32, and I get a 2.32 radians per second. All right, someone tell me when you got the other ones done here. I'll put them on the board for the people zooming in.
Is that symbol that you wrote for rotational?
This,
Yeah.
it's a lowercase omega,
Oh,
kind of looks like a butt.
okay. I thought it was a lowercase omega.
Mhm. Uppercase omega is for like ohms, resistance and electricity. Your partner right there knew that. Have they got the velocities yet? Do I have to calculate them all? What? This one's 1.07? Okay. Any others?
Quick question, how do you get from, how do you find the velocity?
This?
Yeah.
We're using this equation here.
Oh, yeah.
This one's 1.35.
I think that was.
So 1.07 divided by 0.32. This one should be 3.34 radians per second. 1.35 divided by 0.32. This one should be 4.22 radians per second. Those should be all of our angular velocities, I think. Okay. Good. We ready to predict them? Got it ready to go? All right, here we go. Percent errors on anyone that don't come out perfect. No pressure. Got it going?
No.
Going now? Oh, okay. Yeah. Yeah, figure out what's happening. Going now? Okay. Okay, so we're stopping it whenever it starts to just barely come off the pole. That'll be the perfect velocity. It's gonna be, we're gonna get more and more accurate as we get steeper probably. 2.21. Not too bad. 2.21. Get a percent error between those. Subtract them. I don't care which order. Subtract them. And you're going to divide by this one because this is the one we predicted from math. So theoretically, this should be this. Right? This thing out here is our experiment. So subtract those. So basically be 0.11 divided by 2.32 times 100. And get a percent error there. Here we're going up to 20 degrees. Anything under 20% here, I'm happy with. 3.25. All right, that's pretty good. And we'll do a 30. We'll see. My prediction is our percent error will get better every single trial. That was a steep track right there. Okay. 4. 4.00. Okay. All right, anybody get the percent errors for me? 5%? 3? Two divided by 4. Yeah, that last one was really, they didn't drop fast. Let's do that last one again. Let's try that.
Ow.
4.05, that'll be better. Basically 4%. You can keep last if you want. 4 point, I say 4.07.
4.05.
All right. I believe that's all we have to do for that. Okay, questions? All good? Okay, so we're gonna, NASCAR 3, we'll be deriving, and we'll be using all sides of this triangle. Okay, because we gotta include that all, so that's gonna be a little trickier. We'll do that and that experiment, and then we'll be done with the NASCAR inquiry. I'm not sure we're doing that other inquiry or not. I'm gonna have to pick some things that probably just skip. So we gotta get through all those units. Otherwise, I can't give you the college credit. Gotta get to the trick. Yep. We're gonna get through all of them, yeah. Just maybe not as good as we normally would get through.
I also
Take a lot of time sometimes. You know, we gotta skip. We do. Fluid dynamics is actually an online one. I do. You work on it on your own. I'll introduce it here in a little bit. And
I heard Rocket, this is right.
it's actually optional. You don't actually have to do it unless you want to be on a Jedi Council. There's no way you can be on a Jedi Council
I'm gonna go check up on.
for the end of the year. You know, when you get these awesome Jedi awards, keychains, bring on the Jedi Council.
There's only 3 people on it.
Last year there was only 3.
I want to be on it, but I
Luca,
also.
Emma, and
It's gonna be a lot of fun.
Oh, so you give them
the-
you give different ones for.
Monica.
replacement.
Oh, there's a typo. It's not
All right.
I really want to be on the so bad.
Okay, online people. Did that work or not? Let's see, chat. Hey, Mr. Herman, I have a dentist appointment. Oh, you know, I need to leave at 1:45. Okay, so they're gone. Okay. If that didn't work, any of you need to, is there anybody on here still? Yeah, if that didn't work, someone tell me. I recorded it also, so
Yeah, it
trying to
worked.
think of how I can do this for the online people.
It worked well.
See ya, everybody.